So we talked about 5 quantities we might be interested in keeping track of when we're dealing with a kinematics problem between 2 points in time. So our average kinematics problems. The first 2 of those were the change in position and the average velocity. So let's talk about those 2 quantities. So first, the change in position. It's also called the displacement. It is a vector subtraction problem, so it's the final position vector minus the initial position vector, just like any change in quantity, final minus initial. In this case, again, we're subtracting position vectors to get the change in position. And so what does that picture look like? Well, let's assume that we have an object that's initially at some point that has coordinates x initial, y initial. At the end, so at the final time, it's at some second point that has the coordinates x final, y final. And so from the rules of vector subtraction, we know that the displacement, or the change in position, is going to be the vector that runs from the tip of the initial vector to the tip of the final vector. So the displacement in this case runs from x initial, y initial to x final, y final. To find the components of that vector, well, if we have a 2-dimensional problem like this, then we're going to need to break up that problem into 2 component equations. So there'll be one for the x components, where we find that the change in the x component of the position, which we'll also call delta x, is just going to be equal to x final minus x initial. Or the change in the y component of the position, which we'll also call delta y, that's going to be y final minus y initial. So again, we have one equation for each relevant dimension in the problem. So if we've got a 2-dimensional problem, which is many of the ones that we will deal with, then we're going to end up with 2 equations. Practically, when we go to set up those 2 equations, we're going to do what we typically do with vector problems, and we're going to start by breaking those vectors up into components. We'll set up a table, as we often do, to try and help us set that up. So again, we're going to set up the equation that the change in position is equal to the final position vector minus the initial position vector, and so that's what our table is sort of set up to represent. So the change in position is equal to the final position vector minus the initial position vector. So notice I've got the final on top, the initial on bottom, because that's consistent with I'm going to take these components and subtract the second set. So to set up, so I need to break those 3 vectors up into components. Again, for the change in position vector, I'm just going to leave that as delta x and delta y. That may be something I know, or it may be more likely situation is that those are my 2 unknowns within the problem. For the final position vector, well, if I know where the object is located and in what direction from the origin, again, I can break that vector up into its x and y components. The initial position vector, if I know, again, how far away from the origin and in what direction the object was located initially, I can break that position vector up into its x and y components. And so then I can just set up my 2 equations. So that the column on the left will give me the x component equation. The column on the right will give me the y component equation. So delta x is equal to x final minus x initial, and delta y is equal to y final minus y initial. So as with any of our vector problems, again, it's just we're going to set up the component equations. We're going to have one for each dimension. In this case, we have both an x and a y. Now, once I've calculated delta x and delta y, so that means that I know the x and y components of the change in position. Well, if I know the x and y components of any vector, then the 2 things I can do with that information, one is I can calculate the magnitude, the second is I can calculate the direction. So as we often do, I'm going to Pythagorize these 2 components. So the magnitude of the displacement vector is going to be equal to the square root of delta x squared plus delta y squared. That's going to tell me how long the change in position vector is. If I want to know its direction, well, again, I'll define an angle. In this case, I'll call that angle theta. I've defined theta relative to the x-axis, which means I want to put delta x the x component in the bottom of my ratio, and so I'm going to have that the theta is going to be equal to the inverse tangent of delta y over delta x. So I've got y component over x component, so that's going to give me an angle relative to the x-axis. I'm going to end up, my calculator is going to tell me something that's less than 90 degrees. It's going to tell me something that happens to be positive. And so when I report this, again, to report it correctly, I want to make sure that I say that theta in this case happens to be some angle theta below the negative x-axis, because given my choice of coordinate system, both my x and y components for the displacement are negative. So the negative delta y tells me below, and the negative delta x tells me I want below the negative x-axis. So that was the change in position, or the displacement, whichever one you want to call it. They're the same thing. To calculate the average velocity, again, what you'll notice is it's still a vector subtraction problem. And so I'm going to start this in exactly the same way that we just worked the change in position problem. So I'm going to start by calculating the components of the change in position. The added detail here is that I go from talking about the change in position to the average velocity by caring about the time. So the average velocity cares about the time it takes to go from one position to the other. The change in position doesn't care about that time factor. So when I come back to calculate the average velocity, I'm going to work my change in position problem and then just add this extra step of dividing the components of the change in position by the chunk of time between the initial and final points in time. So again, I have two relevant dimensions in the problem, so I'm going to be able to set up both an x and a y equation. The x equation is going to let me solve for delta x over delta t. The y equation is going to let me solve for delta y over delta t. And again, one equation per dimension. If you've got a two-dimensional problem, we're going to set up two equations. So practically, the way that I'm going to solve this problem is, again, I'll set up my table for the position vectors. So even though I'm calculating the average velocity, it's important to understand I'm not using velocity vectors to do that. I need to use the position vectors to do that. So here I'm setting up my change in position problem just like I did before. I've got my x column to give me what's going on with my x components. I've got my y column to give me what's going on with my y components. And again, I've still got the equation that, or I'm still setting up the two equations that delta x equals x final minus x initial. Now I just need to take that equation and divide by that t final minus t initial, that delta t chunk of time. For my y equation for the average velocity, I'm going to do the same thing. I'm going to start by doing the change in position, so y final minus y initial, and again divide by delta t, that extra chunk in time. Just like before, once I know the two components of the average velocity vector, I can Pythagorize to get the magnitude. So in this case, I'm going to Pythagorize, and so I'll have the square root of the x component of the average velocity squared plus the y component of the average velocity squared. That's going to give me the magnitude of the average velocity vector. And again, I can define an angle. We'll call it theta again. We'll define it relative to the x-axis again. And so I'll use the inverse tangent of y component over x component. Again, I'm going to get an angle that happens to be below the negative x-axis, since both my x and y components of the average velocity vector are negative. So you'll notice that that angle theta looks pretty similar. And so to think about that, let's come back to our average velocity equation. And so we'll notice that what it says is, I can rewrite this, and instead of thinking it as the vector delta r over delta t, so the displacement divided by my chunk in time, let's factor out that time element. And so I can put 1 over delta t out front times the vector times the displacement vector. And the reason this is interesting is because now I have an equation where I create a new vector, the average velocity, by taking an initial vector, the change in position, and multiplying it by a scalar. And I notice that because delta t is always positive, 1 over delta t must be positive, so I'm multiplying the change in position vector by a positive scalar. And from what I know about multiplying vectors and scalars, that means that the direction of the average velocity has to point in the same direction as the change in position. So it is always true that the average velocity vector and the displacement vector point in the same direction. Right? They have to, simply because of the way the average velocity vector is defined.